The fundamental theorem of calculus really gives us a new opportunity for notation. It develops, well, first of all, we all know the fundamental theorem of calculus. It illustrates a beautiful relationship between the area under the curve of a function and its antiderivative. Oops, do I even know the fundamental theorem? So the area under the curve of a function, that's what this represents. A lot of books and sort of teachers out there will do the fundamental theorem a disservice by attributing this symbol right here to an antiderivative. I think that's wrong. This symbol, first and foremost, is the area under the curve. That's what this represents. It is an elongated S for sum, given to us by Leibniz, of course. And then it happens to be the case that the area under the curve of a function is heavily related to the antiderivative. But it doesn't go the other way around. The fundamental theorem gives us the relationship between the area under the curve, that's what this is an area, and the function for which you are taking the area under the curve of, its antiderivative, this capital F right here. This is the fundamental theorem. This is surprising. This shouldn't be made light of by simply attributing this symbol a priori to an antiderivative. Anyway, this is a little bit of my rant. One time I was talking about, as I always do, I was expressing how amazing the fundamental theorem of calculus is. And I said, you guys, it's very, very surprising that the area under the curve is given to be, or is found using the antiderivative. And one of my students said, well, isn't that obvious? That's what that symbol means. And that that was my villain arc, so to speak, because all of a sudden I was like, whoa. This symbol and this connection is getting downplayed severely because this symbol is used as the symbol for the antiderivative, a priori, the fundamental theorem of calculus. Okay, so as long as we're all convinced, all of us watching this video are very convinced that this first means area under the curve, and as a huge surprise, it's related to the antiderivative, I'll be perfectly happy. So this is the area under the curve. By happenstance, and well, not by happenstance, by the beautiful fundamental theorem of calculus, it is related to the antiderivative of the function. To our great joy and surprise, the area function, the integral function, the accumulation function is severely and heavily related to the derivative function or the derivative operator. So this fundamental theorem of calculus, now that we have this connection, now that we've fully proven this connection, it introduces a new opportunity for notation. And that is given to us in this box. We have new notation. The derivative of a function, capital F of x, is equal to lowercase f of x. If and only if, so this is notation we are introducing right here. This is not a theorem or anything like this. The integral, or the antiderivative of lowercase f of x dx, with respect to x, is how we would read this, is equal to capital F of x plus c. We have to include this plus c because when you take the derivative, of course, we all know that the derivative of a constant function is going to be 0. So if we want to anti-differentiate a function lowercase f of x, we have to include the possibility that we had a straggling plus constant hanging out along the way. So this is new notation that we have, and we use this symbol now. Now that we've proven the fundamental theorem of calculus, we are granted using this symbol that if we want to find the antiderivative of a function f of x with respect to x, then we can write that using this symbol right here. I'll show a few examples here. Just kind of getting used to this box here, what this is saying. Another way we can write this sentence right here, the derivative with respect to x, that's how we would read this, of e to the x squared is, of course, as we know, because of the chain rule, 2x times e to the x squared. But with this new notation, what we could say is the antiderivative of 2x e to the x squared. Notice I'm writing this part down inside the antiderivative. And the antiderivative with respect to x, notice that there's sort of an analogous idea. With the derivative, you have to tell me what variable you are differentiating with respect to. The same story goes with the antiderivative. You have to tell me what variable we're anti-differentiating with respect to. So again, I like to say, how I like to explain this symbol is this asks what function gives us the derivative of 2x e to the x squared. Notice that this sentence tells us the answer to that. This function does. And then you might say, okay, well, I'm going to write that function down. And then, of course, that is not the entire story because we could have added any number right here, like plus or minus 4 or whatever we wanted. And when we took the derivative in this situation, that would have disappeared to 0. So we want to capture all possibilities by adding what I call a constant of integration. That's what that is. And again, another thing to say here would be, if somebody asks you to integrate, that is now, because of this fundamental theorem of the calculus, that's the same as asking to anti-differentiate. So this asks the question, what function has a derivative of 2x e to the x squared? And this part inside the integral, I've said this before, but that is what I call the integrand. All right. This blue part tells us with respect to which variable we are anti-differentiating. Let's get a little bit more practice. But again, we want to see this as asking a question. What function has 2x e to the x squared as a derivative? And our answer is a whole class of functions. That's e to the x squared plus any constant of integration. All right, let's get some more practice. So this is kind of an opposite question. Well, this is a good example because this asks, what function has 1/2 x to the 7th minus 4x to the 5th plus 1 as its derivative? So this is like saying somebody already took a derivative and landed at this blue function right here. So some mystery function has this blue underlined function as a derivative. And if you have a polynomial function like this, where you have like x's to an exponent and things like this, what you need to do is undo the power rule. So recall that the power rule says, I can derive it kind of quickly. If I have something like this, x to the power of alpha, and I want to take the derivative with respect to x, that is going to bring me here. I needed an equal sign here. That's going to be alpha times x to the alpha minus 1. And that is true for all real numbers alpha. But look at what this implies. This, of course, is as long as alpha is not 0. This implies that 1 over alpha times the derivative with respect to x of x to the alpha is equal to x to the alpha minus 1. But now what I'm going to do is I'm trying to come up with a sort of a formula here that we can use. What I'm going to do is maybe beta equal, I will go with alpha plus 1. Oh, wait, no. Is that what I want? Hold on, let me think. No, beta equal alpha minus 1. I'm going to let beta equal alpha minus 1, and let's just ask how that changes things. Notice this implies that alpha is equal to beta plus 1. And how will that transform this equation right here? Well, first of all, I know something about differentiation. This 1 over alpha can scoot inside the derivative operator, and that will take, before I do any substitution, that will imply that the derivative with respect to x of 1 over alpha, x to the alpha, is equal to x to the alpha minus 1. But now I'm going to use this sort of change of constants here, and let's just see how this changes. This implies that the derivative with respect to x of 1 over alpha is the same thing as beta plus 1, so I'm going to write beta plus 1, and again, this implies this, times x to the beta plus 1, and that is going to be equal to x to the beta. And the whole point of what I'm saying is using this new language with the box that we had up there, this implies that the antiderivative or the integral of x to the beta dx, this sentence right here, tells us that this integral or this antiderivative is the same thing as this thing in this operation right here. So that will be 1 over beta plus 1 times x to the beta plus 1. Of course, this is as long as beta does not equal -1, which says the same thing as long as alpha does not equal 0. And of course, we want to include that constant of integration. So this tells us a whole lot. And let me write beta does not equal -1 because we'll have to think about that case separately. Because now what we can do is, well, there's a few things. I like just doing it logically and saying, hey, what function has this thing as a derivative? And you can do it in one fell swoop. But if you're not quite seeing that yet, what you could do is use your integration rules and say that this is the same thing as 1/2 times the integral of x to the 7th dx minus 4 times the integral of x to the 5th dx plus the integral of 1 dx. All right. And now with each of these pieces, this piece right here, this piece right here, and I guess I could do it with this piece right here, but I'm going to use a different rule. What function has a derivative of 1? That's easy enough. With all of these, I can use this rule right here. Notice that I have something that looks like this right here. Again, I have something that looks like this right here. I have something that looks like this right here. And I know what the antiderivative of 1 is. It's just going to be x. So I can use this rule for all three of these pieces. And of course, that's going to get us right here. This is going to be the same thing as 1/2 times, so my b in this case, or my beta in this case is 7. So I'm going to have 1 over 8 times x to the 7 plus 1, which is 8. So that's 1 over 7 plus 1 times x to the 7 plus 1. So hopefully that makes sense. I'll have 1 over 8 times x to the 8th. And you might be like, well, where's the plus c? What we could do is I'm just going to have a plus c from this part, and then I'm going to have a plus c from this part, and then a plus c from this part. I can use my field axioms, the associative property, the commutative property, to gather all of those constants of integration up in one final plus c at the end. But let's use this rule here, minus 1/4. It's going to be 1/6 x to the 6th plus x. And then, of course, plus c, and I can simplify this as such. That's the same thing as 1 over 16. X to the 8th power minus 2/3 x to the 6th power plus x plus c. So this is a function. What we just said, overall, this is really important. What we just said right here is when I take the derivative of this function, if all went well, I'm going to get this function in blue. Right? So let's just see how that would work. I bring the 8 down. That'll give me a 1/2 x to the 7th, because with the power rule, I have 1 less than 8. Oh, sweet. And then I bring the 6 down right here using the power rule. That's going to be 2 times 6/3. That's going to be -4 times x to the 5th. Oh, nice. All right? So again, I'm taking the derivative of this function to check my work. Of course, the derivative of x is just 1, and the derivative of a constant is just going to be 0. So this is indeed the entire class of functions that give us this as a derivative. And a great question would be, those of you that are mathematicians in the making, how do you know that we only have to, or how do we know this is an exhaustive sort of representation of all antiderivatives of this thing right here? That is a result of the mean value theorem. I'm a huge proponent of the mean value theorem. As I say, I can't emphasize enough how important that theorem is, but we know that if two functions have the same slope everywhere, then they have to differ by a constant, and only a constant, and that's because of the mean value theorem. Okay, so this is a question about differentiation, I guess, but this is also a question about the antiderivative and this new notation. Of course, hopefully we're all aware that to anti-differentiate this, we'll have 1 over 2 root of the inside function, the natural log of z here, times the derivative of the inside function, but the derivative of 1 plus the natural log of z is just 1 over z. And I can simplify this as 1 over 2z times 1 plus the natural log of z. And I think what I'm trying to say here is there's another way to write that. That implies that the antiderivative of 1 over 2z times the square root of 1 plus the natural log of z, dz, is equal to the square root of 1 plus the natural log of z plus c. All right, so you see the relationship between this guy and this guy? Well, it's given right here. Here's the green guy. Here's the yellow guy. There's kind of like that inverse relationship between anti-differentiation. Again, that's anti-differentiation and differentiation, of course. All right, let's see more. All right, now we're kind of begging a nice spurring point for the rest of today's lecture. What if I wanted to ask what is the derivative of f of g of x? Hopefully that's a review for everybody, but this is going to be the same thing as f prime of g of x times g prime of x, right? That is simply the chain rule. But with this new notation, another way I can say this sentence is the antiderivative of f prime of g of x times g prime of x dx is equal to f of g of x plus the constant of integration. Now, to kind of give us a hint for what this class is going to be about, what this session is going to be about, what I could do is rewrite this. Here's how I'm going to rewrite this. I think what I can do is let a new function u, which is a function of x, be equal to g of x. All right? Now, what this implies is that the derivative of u with respect to x is g prime of x. All right? I simply took the derivative on both sides of this equation. Now, with our definition of differentials, okay, now you're going to be tempted to say what I just did was multiply both sides by dx. That is not what I did. But this sentence notationally means the same thing as this sentence right here. In fact, this is the definition of the differential du. Du is equal to g prime of x dx, all right? Now, what I want to say here is this. All of a sudden, I've made a few new sentences, and I think my original integral can transform. All right, so I have something in green right here, and then I have something in yellow right here, all right? Really, really crucial. Check this out. Or I could even do better than that. Notice that this red part right here is sitting in my integral right here. So what I think I can do is replace this red part with this part right here, du. Not only that, I have this green part right here. This g of x is also sitting in my integral right here, as well as right here. So let's just do a little bit of translation here. How is my integral going to transform? I think what that says is that the integral of f of u, okay, again, what I just did is I replaced this g of x with u, because that's what I named it, times du, again, this red thing right here is necessarily du once I make this substitution. F of u du is equal to f of u, I'm sorry, f prime of u. Sorry, I missed that. I missed the prime here. Is equal to f of u, so close to being insulting, f of u, plus c, all right? That is how this transformation goes. And this is going to be very, very wildly helpful. The key here is this. What we want to learn to do is pick up on when somebody took the derivative of a function using the chain rule. And a way to find out, or a way for us to uncover this and translate this into a much simpler integral, just f prime of u du is very easy to anti-differentiate. This is very easy to anti-differentiate, but it is simply this uncovered. What we can do is what I call the substitution method. The substitution method. And simply let some part of our integrand here be equal to u. In this case, we use g of x. And it allows us to anti-differentiate this much more smoothly, okay? So let's see this in action. This is simply us, or me, motivating what we're going to do next. What we want to do is pick up on when somebody has taken the derivative of the composition of functions. We want to notice when we have the result of the chain rule inside of the integral. This process of the integral of some function with respect to x, all we're doing, this is called indefinite integration or anti-differentiation. All we are doing is asking, hey, what function has this thing as a derivative? And this is one of our first tools to make that job, or to make that quest, much easier. Let's see it in action. I think I had some examples. Here we go. All right, so we have some mystery function. We have the integral, or we need the antiderivative of x squared plus 1 to the third power times 2x dx. At the beginning, I seriously think the best thing to do is just take a gamble. We know that 2x dx is sitting right here. We know that 2x dx is sitting right here, and that is the derivative of some function, namely x squared. But not only is this the derivative of x squared, is 2x the derivative of x squared, it's also the derivative of x squared plus any number. So why not just let us let x squared plus 1 be u, and let's just see how this integral transforms. Let me say that better. Let u equal x squared plus 1. Well, what would that necessarily entail? That necessarily entails that the derivative of u with respect to x is 2x, right? But that necessarily entails, another way to write this would be du is equal to 2x dx. But look at what I have. In yellow here, I have 2x dx. Oh, that's sitting right here. In green here, I have x squared plus 1. Oh, that's sitting right here. So I think this integral can immediately transform to the integral of u to the third power. Again, that is because another name for x squared plus 1 is u. So this is simply u right here. That is u. And this is, right here, du. That whole thing. So how does this integral transform? I have the antiderivative of u cubed du. Okay, but that's easy. I can just use the reverse power rule here. That's going to be 1/4 u to the fourth power plus c. But this is kind of like me answering a question that was posed in English in French or something like this. So what I need to do is sub back in my original name for u. And that is going to be the same thing as 1/4 x to the second power plus 1 to the fourth power plus c. Again, I have u right here. This is u because of this relationship right here. All right, so we just did our first nice antiderivative. Let's get more practice. All right, again, I think what we can do from the get-go is, honestly, what you should do at the beginning, once you're used to this, is just make a guess. But here's what I'm realizing. I have 5z right here, and I know the derivative of 5z is 5. So it seems like the derivative of this function 5z is sitting in the integrand right here, and that is a giveaway. That if you see a relationship between a function and its derivative inside your integrand, then it's a good gamble to let this be u so that du is sitting right here. So let's try that. I'm going to say let u, and by the way, there's nothing special about u. You can use whatever you want for this variable. You can use star, you can use smiley face, you can use x in this case, since we're integrating with respect to z. That would be a little bit horrendous, but actually not really, honestly. You could definitely do that. So I'm going to let u equal 5z, and I think that immediately implies that the derivative of u with respect to x is equal to 5. Oh, you see, I just blundered. We have a function with respect to z, so let me try that again. The derivative of u with respect to z is equal to 5. And that tells me that du is the same thing as 5 dz. All right. And how does this transform? Look at what I have. I have 5 dz sitting in my integrand, 5 dz. So I think this in red comes together in the form of du. Notice that that's just du, right? And then here in green, I have 5z sitting right there, but 5z is the same thing as u. So how does this integral transform? I think this integral is equal to the integral of 5 dz gets wrapped up in du, and you want du to be in the end or after your integrand. And all that's left here is I still have the cosine. Cosine, I don't want to write 5z here, but what I want to write is u. Okay. Now I want to find a function whose derivative is the cosine of u, but I think we all know and love that function. That's going to be the sine of u plus c. But again, I don't want to answer an English question in French, so I want to sub back my definition of u. All right, let's get more practice. All right, in some cases, it's not obvious what form, actually in this case, it is pretty dang obvious. But sometimes you have to just guess for some function for what you want to assign u to be. So in this case, what I'm going to do is simply let u be the thing on the inside of this radical right here. So after I do so, let's just see where this takes us. I'm going to let u equal 2x minus 1. That, of course, tells me that du is equal to 2 times dx. You might look at this and go, oh, shoot. I only have the dx right here. I need a 2 times dx. So what you could do is, like all good mathematicians do, is simply say this integral is the same thing as 1/2 2 times the integral. And of course, using some integral laws, that is the same thing as 1/2 times the integral of the square root of 2x minus 1 times 2 dx. We just magically forced our derivative here to show up in our integral. So again, why is that powerful? We have 2 dx right here. Another name for that is du. So that object is du. And then right here, inside of the radical, I have 2x minus 1. Another name for that is u. So how does this integral transform? We have 1/2 times the integral of the square root of u du. Oh, but that is the same thing as 1/2 times the integral of u to the 1/2 du, right? And that is the same thing. We can use our antiderivative power rule here, that thing with the beta and the alpha. This is the same thing as 1/2 times the integral of 2 times u to the 1/2. Here, let me show a little more steps here. That's going to be 1 over 1/2 plus 1 times u to the 1/2 plus 1 plus c. And that's inside the parentheses. This is the same thing as 1/2 times, simplifying this fraction, I'm going to do it quite quickly, just because hopefully we've all sort of seen this before. That is going to be 2/3 times u to the 3/2 plus c. And this is the same thing as 1/3 times u to the 3/2 plus star, or I can call it C1 or smiley face. Just anything to differentiate from this C, because technically when we distributed the 1/2, we generated a new constant. Honestly, if you kept that as just C again, I wouldn't bite you or take away points too hard, but just technically that is a different constant. So for mathematical completeness, you want to differentiate it somehow. You can use whatever you want. I use the subscript of 1, but maybe just like a C star would be better. Of course, we don't want to answer a English question in French, so I'm going to resub back in what U was. It's going to be 1/3 2x minus 1, because that is the same thing as U, right? U is 2x minus 1 to the 3/2 plus C star. Done. Getting more practice. Oh, things just got a little bit trickier. Shoot. I'm going to let U be the same thing. That, of course, implies that the derivative of U is equal to 2 dx. And shoot, but I have x here. What am I going to do with x? So last time I could multiply top and bottom by 2, but I'm not going to have my derivative sitting in there. Well, actually I will. Maybe that's what I should do first. But what I'm actually going to do this time is simply isolate dx. Because I have this yellow dx right here, I can just get this yellow dx right here by itself by dividing both sides of this equation by 2. So now I know what this is. Like that is 1/2 du, right? dx is 1/2 du because of this relationship right here. This guy right here, 2x minus 1, is the same thing as u. But check this out. I want to figure out what x is. That is a missing piece. I don't know what x is, but you guys, don't forget your algebra. Literally, we learned algebra. I would argue that we learned algebra so that we can do calculus. Isolating for x in this equation, or maybe I should do it separately like this. I think we're all good. Add 1 to both sides. Divide both sides by 2. So that tells me that u plus 1 is equal to 2x. But that tells me that u plus 1 over 2 is the same thing as x. Check that out. X right here. X right here. So apparently this x can be replaced with u plus 1 over 2, transforming my entire integral to u plus 1 over 2. Again, that was the thing in blue, right? Times the integral of u, again, I just replaced that green object, times dx, but apparently dx is the same thing as 1/2 du. All right? Powerful, powerful stuff. Now what I have is everything in terms of u. You want to be very careful when you're doing this anti-differentiation. You want consistency across the board in your integrand. Notice that the only variable that showed up with this original integral was x. You want to make sure that when you write the next substitution, that the only variable that shows up is u, or whatever you chose your substitution to be. Like I said, this could be whatever the heck you want. It doesn't have to be u. Now using integration rules, that is the same thing as 1/4 times the integral of u plus 1 times the square root of u du. That is the same thing as 1/4 times the integral of u to the first power plus 1 times u to the 1/2 power. I'm going to show a lot of work here. You can certainly skip a lot of these steps if you feel that you know what you're doing. Of course, this is the same thing as 1/4 times, no calculus here. I'm going to use the distributive property. That's algebra. This is going to be u to the first power times u to the 1/2 plus u to the 1/2 power times du. That is the same thing as 1/4 times the integral of u to the 3/2. Hopefully we remember our exponent rules. Plus u to the 1/2 du. And to make things go a little bit faster here, I'm going to use that anti-power rule a little bit faster. Here's how I do it. What I do is I start by adding 1 to this exponent right here. So that's going to be u to the, 5/2. And then I simply multiply by what is going to cancel this out. I multiply this thing by what's going to cancel this out when I bring it down via the power rule. And that's, of course, going to be 2/5. You simply flip it upside down. You always just flip this upside down. Same story here. I first add 1 to the exponent. So 1/2 plus 1, that's going to be 3/2. And then, like I said, I just flip this. That's going to be 2/3 I'm going to have to multiply by. Plus c. All right, that is the same thing as 1/10 u to the 5/2 plus, let's see, 1/6 u to the 3/2 plus some smiley face here. Don't care what it is. And that is the same thing as 1/10 times, I sub back in u. Remember, I don't want to answer a question in a different language. That will be 2x minus 1 to the 5/2 plus 1/6 2x minus 1 to the 3/2 plus that constant of integration. Call it good. See what's next. Okay, so this is absolutely huge. All of a sudden, we are asking, so this is a huge shift. I really want us to hear this. This is an entirely different type of question. Notice the difference between our original question right here, or the question we had before right here, and this question right here. This is asking for an antiderivative, okay? And the reason this is asking for an antiderivative is because of the new notation that we had, right? This question is not asking for an antiderivative. Well, to answer the question, we will need an antiderivative. But what this question is asking for is the area under the curve of L over the square root of 2L minus 1. Why is this different than what we had before? Because this one has what I call bounds of integration. This immediately tells us that this is looking for a number, an area, where this question right here was not. This was asking for a function right here. This was asking for an antiderivative, an entire class of functions. This thing right here, because we have the 5 and the 1, we call those bounds of integration. This is asking for an area under the curve. And also, you should always double check and make sure that this makes sense as a question. For instance, this function is not defined at 1/2. So we better make sure we're not integrating over an interval. Notice the interval in this case is going to be 1 to 5. We better make sure that 1/2 is not in that interval. So we're lucky in this case that it is not. But, so, like I said, this is asking an entirely different question, but luckily for us, we can answer it using a similar method. We can do a substitution method to answer this question. Why? Because of the fundamental theorem of calculus. All we need to answer these disgusting limit of a Riemann sum area questions is an antiderivative. This question becomes very, very easy because of the fundamental theorem. So I just need an antiderivative of this function on the in the integrand to find the area here. This is asking for an area. Please be reminded of that. And we are going to answer this question, which is, as it's posed, very hard. Because of the beauty of the fundamental theorem, this question becomes very easy. I don't know how to emphasize that enough. So what I'm going to do is I'm going to let u equal 2L minus 1. Now, notice these bounds are with respect to x, or excuse me, not x, L in this case. This is L equals 1. I want the area under the curve L over the square root of 2L minus 1 from L equals 1 to L equals 5. So this is also with respect to L. If I want to transform this integral, I need to ask the question, well, what does u equal when L is equal to 1? All right, so here's how I do that. It's not too bad. I simply look at the lower bound. I say L equals 1. What does that imply about u? Well, of course, u would equal 2 times 1 minus 1. Why 1? Because, look, u is given in terms of L. So when L is equal to 1, that tells me that u is equal to 1 as well. Hey, we got lucky there. If L is equal to this other bound, L is equal to 5, that implies that u is equal to 2 times 5 minus 1, which is, of course, equal to 9. So that's really important. When I do my substitution, when I make my substitution and figure out all of these other pieces, I have to switch my bounds of integration, all right? So here, let me color this a little bit differently. Here's my L equals 1, L equals 5, and I want to change these perhaps to green. But I have more work to do, right? I have to also ask if u is equal to 2L minus 1. I think, first of all, that implies that u plus 1 divided by 2 is the same thing as L. But also it implies that the derivative of u with respect to L is equal to 2. All right, that's really crucial. And now what that implies, of course, is that 1 over 2 times du is the same thing as dl. And let's see if we have all of our substitutions handy. Let's see, what color can I use? All right, we got dl right here. So dl apparently is 1/2 du. We have our green u at the very beginning. Let me underline this. Okay, 2L minus 1, that's it right there. That is also known as u. But we also have that L is right here. Oh, look, there it is. That is the same thing as u plus 1 divided by 2. Again, it's very important that when I make my substitution, oh, and I should also say this, u is the same thing as 1 here. U is the same thing as 9 here because of this relationship. When I am, watch what I'm about to do. I'm about to rewrite this integral with a mega equal sign. I am saying that the area under the curve of this function with all the relationships with L is the same number as this integral, or as this area. So again, I just want to emphasize the substitutions I made. All right? I did all those substitutions, and now I can literally, once I've done this successfully, I can forget the original question. Because of the power of this equal sign, I can forget the original question and simply simplify this new area question in terms of u. All right? This is the same thing. Notice I have a 1/2 right here and a 1/2 right here. I can take both of those out. Then I'll have the integral of from 1 to 9, or the area under the curve from 1 to 9 of, it'll be a u plus 1 divided by the square root of u times du. All right. And this is the same thing. Watch this carefully. This is the same thing as 1/2 times the integral from 1 to 9 of u plus 1 divided by u to the 1/2. All right, that's just a change in notation. This is the same thing as 1/2 times the integral from 1 to 9 of u plus 1 times u to the negative 1/2 du. That is the same thing as 1/2 times the integral from 1 to 9 of u times u to the negative 1/2 plus u to the negative 1/2. Again, that was a algebra step. Wait, don't I have... I messed this 2 up. I don't know if you guys noticed this. This should be a 4. Because I had 2 of those in the denominator. My bad. All right. That is the same thing as 1/4 times, okay, so check this out. That is the integral from 1 to 9 of u to the 1/2 plus u to the negative 1/2 du. Watch this notation. I need a function whose derivative is this thing right here. This is the same thing. I'm going to write 1/4, and then I'm going to open up a bracket like this. This is simply notation, and I'll show you what it means if you don't remember. But what I want to do is find an antiderivative of u to the 1/2 using my power rule. That is going to get me 2/3 u to the 3/2. Again, I simply added 1 to the exponent. 1/2 plus 1 is 3/2, and then divided by the new exponent. Same story right here. This is going to be 2 times u to the positive 1/2. And then I'm going to evaluate this from 1 to 9. Okay? Now, I just used the fundamental theorem of calculus. And I'm going to say this loudly every time I use it. I just skipped so many steps because of the fundamental theorem of calculus and the relationship between areas and slopes. All right, this is the same thing. So what does this notation mean? That is a good question. What does this bracket with this mean? Well, that's the same thing as 1/4 in parentheses. What I'm going to do is rewrite this function 2/3 to the 3/2 plus 2 to the, or 2 times something to the 1/2. And what I'm going to first plug in is 9. Close parentheses, subtract the same thing. So that's going to be a 2/3 times something to the 3/2 plus 2 times something to the 1/2. Close parentheses. It's just this time I'm going to plug in that 1. Let's see how this simplifies. This is the same thing. It's 1/4. This is just heavy math here. Maybe I won't do this part because this is simply, I'll do this one. This is going to be, I'll simplify it a little bit, but this is, I feel like, a waste of my video time. The square root of 9 is 3. 3 to the 3rd power is 27 plus 2 times 3 minus 2/3 plus 2. And we can plug that, simplify that as much as possible. Make sure you reduce your fraction and pose it as a good answer. But that would be it. So check this out. I'm trying to remember how much I have here, and this is all right. All right, so another u-sub. Let's try it. Another example here. Immediately, I'm just going to guess, and I'm going to say, let's just let u equal 1 plus the square root of x. And again, if you're asking, well, how did I know to do that? It's because I've done a ton of these, and I know how this story goes. The way to do this is to get a ton of practice doing anti-differentiation and finding the area under the curve. Notice that this, because we have bounds, is asking about the area under the curve. We also better make sure that x is not 0 or negative. It is not. This takes getting used to. I see the future and notice that this is going to help us. But let's pay the consequences of our actions. Notice these are both bounds with respect to x. So if x is equal to 1, I think that implies that u is the same thing as 1 plus the square root of 1, which is the same thing as 2. If x is equal to 9, again, I'm using this one, then I think that tells me that u is the same thing as 1 plus the square root of 9, which is the same thing as 4. All right? But not only does it tell me that, this substitution also tells me that du is the same thing as 1 over 2 root x dx, right? And that, of course, tells me that 2 du is the same thing as 1 over the square root of x dx. Oh, but check that out, you guys. I have that sitting in my integral. So this with this, combined with this, that is the same thing as 2 du. You might not like I am using a few fraction rules to really use that successfully, because you might be like, well, this thing's like in the denominator. How is that the same thing? I am undoing fraction multiplication to declare that I can rewrite this yellow part, as 2 du. But what other substitutions do I have? Look, right here in the parentheses. That's the same thing as u. So I think I already have a transformation of this integral. Again, I'm going to switch those bounds with their new names in the u world. So when x is equal to 1, then u is the same thing as 2. So this lower bound is going to be 2. When x is equal to 9, then u is equal to 4. So this upper bound is going to be 4. This yellow thing is going to be the same thing as 2 du. And then I have divided by u squared. All right. Now, of course, this is the same thing as 2 times the integral from 2 to 4 of u to the negative 2 du. That is the same thing as 2 times negative u to the negative 1. So I just anti-differentiated using that anti-power rule from 2 to 4. And of course, this is the exact moment where I give credit where credit's due. I just used the fundamental theorem and skipped so much work. This is the same thing as 2 times, in parentheses, I will have negative 4 to the negative 1 power minus negative 2 to the negative 1 power. And that will simplify to some number. Easy. Finding the area under the disgusting curve, and I don't have to find the limit of a Riemann sum at all. Very, very powerful. Okay, a few fun results I know I had to bring up when it comes to finding areas as such. Something to remember is this special definition of a function being even. If a function is even, what that means is the function, well, it has a few definitions, and I wanted to talk about both of them. The real definition of a function being even is that f of negative x is always equal to f of x, right? That's what that means for all x values in its domain. All right, that's what it means for a function to be even. But let's look at what that means in a graph. What that means, if I had an xy plane here and I wanted to sort of plot what one of these functions are, if I were to go x in some distance x and find my function, well, that output, it has to be the same as if I go negative x. That's what this means. So if that's true for all x values, what that means is that my function has to look symmetric over the x-axis. In other words, if I were to sort of perforate my Cartesian plane right here and fold it over to where, I don't know, let me draw it kind of quickly. If I were to sort of fold my Cartesian plane, oh, this is going to be tricky. I'm doing all right. Sort of like this. And so this would be kind of like fancy shadow right here. And if this is going to like fold over right here, then the function has to land on itself is pretty much what I'm saying. All right, that might be a horrible illustration, but the function has to land on itself. And what this question is asking, or what this result is telling us, is actually kind of intuitively true. This side right here in red is asking us to find this area. All right, we want to find that area, and maybe let me call this A here. All right, so that's negative A to A. Look at what it says. It's very intuitively true. Both of these are above the x-axis. I think in order to find the red area, what I could do is find this blue area and then double it. This integral right here is this blue area. But to find the red area, notice that I have another sort of piece of this blue area simply on the other side of the y-axis. So to find the entire red area, what I could do is simply take this blue area, which is the integral from 0 to a, and then double it. Put a 2 out front. Those have to be the same thing. All right. So this is the definition of an even function right here. Good review. Hopefully you've seen that before. We will use that a lot in a few of this week's videos. This is the definition of odd. There is also a beautiful, beautiful interpretation for this for odd functions. So the definition of odd would be that f of negative x, so what does it mean for a function to be odd? F of negative x is always the same as the negative of f of x. All right, so what does that mean in terms of an integral? Let me draw an xy plane first. So let's say I were to go out here some distance a, and then I'll also put negative a here. So say this is f of a right here. What this is saying right here is if I were to go to negative a, I have to have this same blue distance, except in the negative direction, all right? And that has to hold for all values. So my function might look something like this. And what we should notice here is that this is simply a 180-degree rotation, right? If I were to simply spin my XY graph 180 degrees, then my function is going to land back on itself, right? By the way, a few examples of, well, let me kind of come up with this result first. So a good question, or what this question is saying, is what relationship do we have for this integral right here? Well, this integral, this red integral, is going to give us this area, but negative, because it's below the x-axis, and this area. You guys probably already see it, but those two areas are the same. This area is the same as this area because my function is odd. And since the integral is going to read this area as negative, the total area of this integral, or the total value of this integral, is going to be 0. This area is going to completely cancel out this area. Also intuitively true. Let me, first of all, give a few examples, and then we'll prove one of these. So a few examples of even functions. So this would be even functions. Y equals x squared. Y equals, I don't know, x to the 100th power. Or x to the 100th. Y is equal to cosine is like the quintessential even example. A few examples of some odd functions. Few examples of some odd functions would be like y is equal to x to the 3rd power. How about y is simply equal to x? Y is equal to tangent of x. And the quintessential example is y is equal to sine of x. So why is this so useful? If you ever spot this relationship, like for instance, if I wanted to find the integral from negative 100 to 100 of, how about, I don't know, sine x all divided by x to the 4th power plus x to the 2nd power plus 1 dx. What you could do is simply notice that this function in here is an odd function. This is an odd function, so I can immediately just state the answer, and it's asking for the area under the curve of this disgusting function. The answer is 0. Done. Don't think that hard. And that is because of the observation that this function on the inside is an odd function. All right, super powerful. I really wanted to prove one of these, but I don't think I have time in this video. Maybe I'll save it for another one. We're already at an hour. Hi. I think I still have to do all this. All right. Find the area of the region bounded by the graphs of 2 minus x squared and g of x equals x. All right, so area bounded by some graphs. We now have the tool of the u-substitution to find things like this, or to help us finding areas because of the fundamental theorem of calculus. We can simply anti-differentiate, and the u-substitution helps us with anti-differentiating. Although in this case, I don't think I will really need to, or we will really need to. All I need is to graph these functions. This is an upside-down parabola, scooted upwards 2 units. This is the function y equals x, perfect 45-degree angle function, and I need to find the area bounded by these two functions. So I need this area. And you might say something along the lines of, okay, well, that kind of sucks because some of it's under the x-axis, some of it's above the x-axis. And I agree, that does kind of suck, but we're going to be a little bit clever here. And notice, just in general, if I wanted to find the area, of two functions, maybe like this and like this. Don't really care what they look like. Let's say I wanted to find this area. Call this A, call this B. So I want to find this area, and you'll be like, oh, shoot. Some of it's under the x-axis. Some of it's above the x-axis. Let me actually explain this in two different ways. What I really need to do, you'll probably already notice, I need to find this yellow area and add to it this blue area right here. So let me name these functions. Let's say this was, let's say this was f of x, and this was g of x. Of course, that yellow area is going to be the same thing as the integral from a to b of f of x dx. Now, this blue area is going to be the negative of the integral of a to b of g of x dx. Notice that this integral on its own is going to give us a negative area because it's below the x-axis. But I don't want negative area. I want the total green area here. So to make that negative area positive, I simply throw a negative on it. But what I want to do, based on the picture, is add the yellow area and the blue area to get the green area, which is what the question originally asked. So what I need, the total area, our green area, as I've said, is the same thing as the yellow area plus the blue area. But I know what both of those are. That's going to be the integral from a to b of f of x dx minus the integral from a to b of g of x dx. But using some of my integral laws, that's the same thing as the area under the curve from a to b of f of x minus g of x dx. And I know that that shaded region is this. The most important thing here is that the function you write first is bigger than the other function or more positive than the other function. And this method will always, always work. Notice that g of x was negative, but I can still use this method. So going back to our original question, that makes this actually quite easy. To find this red area, that red area is going to be equal to the integral from, oh shoot, I have to find these two intersection points. All right, stand by, guys. Luckily, we all know algebra, easy algebra. Set these two curves equal to each other. 2 minus x squared is equal to x. That tells me that x squared plus x minus 2 is equal to 0. That tells me that x plus 2, x minus 1 is equal to 0. So that tells me that this b value is 1. What did I do? This is supposed to be a. This a value is negative 2. So I know my integral is from negative 2 to 1 of f of x minus g of x. Why is this the case? Because this curve on top, the larger or the more positive curve in this interval, so we only care about this interval. Notice that every single time in this interval, my function is above the other. My f of x is above the other one. And so I'm going to write that one first. That's really, really crucial. Dx. All right. So this is the same thing as the integral from negative 2 to 1 of, what is my f of x? This is going to be a 2 minus x squared minus my g of x, which is just x dx. And of course, this is the same thing as the integral from negative 2 to 1 of, 2 minus x squared. You do not need to unnecessarily use the commutative property like I just did, but that's going to get your answer. And of course, if we actually want to find the area, we would simply compute this integral using the fundamental theorem of calculus. But that's easy enough. I'm going to leave that to you guys. Homework right here. Next question. All right, so sometimes the curve is not given to us, and also sometimes we have to decide which function is larger so that we can use this new formula properly. We want to find the area bounded between the intersection points of the curves y equals cosine of x and y equals 2 sine squared x minus 1. Now, full disclosure, and we're only limiting ourselves because these functions oscillate a ton. This probably has infinite area. So we want to limit ourselves to the intersection points that occur within this interval. So what we need to do is set these curves equal to each other to find our bounds of integration. So I'll write that down. To find bounds of integration, we set cosine x equal to 2 sine squared of x minus 1. And we want to solve for x here. You might notice that that's a little bit tricky unless you recall your trigonometry. So hopefully you guys are playing along. I left a huge parentheses here where sine squared of x is. And I'm begging us all to recognize that we can rewrite sine squared as 1 minus cosine squared. That implies that cosine of x is equal to 2 minus 2 times cosine squared of x minus 1. That tells us that 2 times cosine squared of x plus cosine of x minus 1 is equal to 0. I just did some quick algebra. Pause and see if you can catch up to the same spot as me. And also, you should pause and make sure I don't make any mistakes. But let's notice that this is a quadratic function in terms of cosine of x. So I can simply factor this. This implies that 2 times the cosine of, okay, let's see if I can get this. Something 1, this one's just going to be cosine of x, something 1 as well, but I have to figure out which one's negative. Nope, that one's positive, and this one's negative. There you go. So that implies that cosine of x is either equal to 1/2 or the cosine of x is equal to -1. And of course, that limits our values for x because we're limited to this interval. I think there's only 2 chances for this to happen, and that is when x is equal to, pi thirds. Yep. And this occurs when x is equal to pi. So we just found our bounds of integration. Now what we need to do is check which function is bigger than the other. So we know our integral looks like this. Pi thirds to pi. I just don't know which one's going to come first, right? And what I need to do is write the bigger one first. So what I could do is simply test a value between these two numbers and plug it into our two functions and see which one's bigger. It's easy as that. So I'm going to use pi halves. The cosine of pi halves, that's easy enough. That's 0. But 2 times the sine squared of pi halves minus 1, that is going to be 2 times sine squared of pi halves. That's going to be 2 times 1 squared minus 1. That's the same thing as 1, which means that this function is going to be the bigger function, right? Which means this function is going to be the one that I want to write first. 2 times sine squared of x minus 1 minus the cosine of x. And this is the area that we need. We need this area. So the question asks for an area. We just found an integral expression for that area. And I am actually right now realizing that, I guess there's a few ways I can do this. Here's what I'm going to do. This is the same thing as the integral from pi thirds. This one might be a little tricky, so I'll go through the work here with you guys. Of negative 1 minus 2 sine squared of x minus cosine of x dx. But you guys as trigonometry experts should stare at that and go, oh, that's the cosine of 2x. And therefore, this is the same thing as the integral from pi thirds to pi of the negative cosine of 2x minus cosine of x dx. This is the same thing as the negative of the integral from pi thirds to pi of the cosine of 2x dx minus the integral from pi thirds to pi of the cosine of x dx. All right. This is the same thing as the, oh shoot, you know what I'm going to do? I'm going to do a u sub. I'm going to say let u equal 2x. That tells me that du is the same thing as 2 dx. Also, if u is equal to pi thirds, if x is equal to pi thirds, and again, what I'm doing is I'm changing these bounds. If x is equal to pi thirds, that means that u is equal to 2 times pi thirds, which is equal to 2 pi thirds. And if x is equal to pi, is bound up here, that tells me that u is equal to 2 times pi. And so, of course, this also implies, sorry, let me get all my ducks in a row here. We got 1/2 du is the same thing as dx. And what that tells me right here, this first integral completely transforms to the negative of the integral. Again, I want to substitute this guy for its new bound, 2 pi thirds. And the upper one is going to be 2 pi. And then what I have is going to be the cosine of u times 1/2 dx, or excuse me, 1/2 du. 1/2 du, it's out of frame. And this other integral stays the same. I didn't do any substitutions in that one. All right, that is the same thing as the negative 1/2 of the sine of u from 2 pi thirds to 2 pi minus, we have the sine of x evaluated from pi thirds to pi. Okay, and you would plug this into a calculator. Of course, I almost forgot. That was because of the fundamental theorem of calculus. Skipped a ton of work taking the limit of that Riemann sum. All right, 2 more I have to do. Big video, guys. Thank you for persisting with me. I need to find the area of the region between the graphs of f of x, which is equal to 3x cubed minus x squared minus 10x, and g of x, which is equal to 2x minus x squared. So first things first, let me use a different color. Set them equal to each other so that we find our bounds of integration. Let's see. Gathering everything on one side, maybe I'll have, this implies 3x cubed. Too difficult. Minus x squared's cancel? That's crazy. Minus 12x is equal to 0. That tells me that 3x times x squared minus 4 is equal to 0. That tells me that x is either equal to 0 or plus or minus 2. All right, so this is a cubic equation right here. This guy right here. This is a cubic equation. It goes something like this. This is a quadratic equation. It's upside down, so it goes something like this. But the issue is that they cross each other 3 different times, which means that they are going to flip-flop in which one's larger than the other twice, or I guess 1 time they will flip-flop. To kind of get a little bit of an idea, I would graph these. We know how to graph these functions. First of all, the x-intercepts of this guy is going to be 2 and 0. And I'm noticing that this will have an x-intercept of 0. Here, let me graph this one better. Oops. Just so I can see the interceptions. All right, I'm really emphasizing my parabola here. So here's my y equals 2x minus x squared. And I have this cubic right here. It's going to look something like this. Okay, so again, what we found was that this value right here is -2 from this part right here. This value right here is obviously 0. And this value right here is +2. But notice that I really need to compute two different areas here, this red area and this blue area. Why? That's a good question. The reason is, so we have this top one is going to be, 3x cubed minus x squared minus 10x. All right, so this top function, well, the top function flip-flops. So here, let me use maybe color here. This function right here is going to be the cubic. So for the red area, the yellow function is above the white function. But for the blue area, the white function is above the yellow function. So if I want to do this properly, I have to split this into two different integrals and then add them up. So again, notice, I don't know why I used y here. This should just be f of x. It's much better. And this is g of x. So notice f for the red function, I have to integrate from -2 to 0. And what I have is that my yellow function f is larger than the other one, which means I want to list that one first. So I'll have f of x minus g of x here, dx. And then for the blue function, what I have is that the white function g of x is above the other one. So from 0 to 2, I have to list g of x first because it is more positive. And of course, the integral that I want, or the area that we want, the question's asking for, is the sum of those two areas. So from now on, it's just plug and chug. I'll leave that as homework. You guys might be screaming at me behind the scenes here. Easy integration to find that area there. I would seriously suggest you do it, but I want to keep this video relatively short. There's one more topic we need to discuss, and it's this question right here. I've sort of went over it, unfortunately, or I drew all over the space for this question. I have the area of the region bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. Okay, so loudly, you guys. This is not a well-defined function in the xy plane. Because notice that, quote-unquote, our dependent variable is x right here, and our independent variable is y. So this is a sideways parabola, and this would be a line, which is, of course, actually, this is perfectly well-defined. But this one is not well-defined. But the question here is, if you have two functions that are in terms of, or if you have two functions in terms of y, whose independent variable is y, the question becomes not which is more, actually, the question is really still the same. But I'll say, in the other case, it's which function is above the other one. For this case, it's which function is more to the right of the other one. So if we have an xy plane, something like this, x, y, and again, these are two curves. We would call these curves, not functions, because they aren't functions. Again, there is a way you can answer this question without graphing it at all, but I think we are well adept in noticing that this is a sideways parabola opening to the left and scooted along the x-axis 3 units. And of course, this would be honestly, what I would do is I would just immediately say, well, that implies that y is the same thing as x minus 1. So that one, this function right here, this function would be a line shifted downwards, 1 unit, whose slope is 1. And we have 2 intersection points. We better crush what those 2 points are. That's easy peasy. Simply set these two equal to each other. So we'll have 3 minus y squared is equal to y plus 1. That tells me that 0 is the same thing as y squared plus y minus 2. I've already factored this one. 0 is the same thing as, oh, maybe I haven't. Yeah, I have. in this video I factored this one. I should have come up with a trickier one. Y minus 1. Of course, that tells me that y is the same thing as either -2 or +1, which tells me that this value down here is -2. This value right here is +1. Okay, and what I want to do in this case is find this yellow area. But to set this up properly, notice that if I want that yellow area, I have to set up an integral with respect to y. So really behind the scenes what we are doing, and this is no joke, it feels heavy, but what we are literally doing is actually stacking up flat rectangles. Instead of rectangles that are upright, we're stacking them up like this. But it's not like I said, the fundamental theorem does not care what variable you are integrating with respect to. We can still take antiderivatives and use the fundamental theorem. So I think what we want, though, is these integrals or these bounds of integration are with respect to y now. So I want to start with the lower y bound of integration. That is going to be -2 here. So this will be -2. And then up to 1. And again, like I said, I want to place, so it's going to look something like this for sure. And notice what I write here, dy. That's really, really crucial. I'm integrating with respect to y. What this means is I literally think about that as stacking rectangles in y direction. But what I want to write in the first one, the first one I want to write is the one that's more to the right, or the more positive in the x direction, right? And that is, of course, going to be this blue function, which is my 3 minus y squared, 3 minus y squared. And then I write my red function, my green function, which is y plus 1. Okay? Then, of course, I would evaluate that yellow area to compute the perfect area right here using the fundamental theorem of calculus. So if you are integrating with respect to y, then you want to first place the function that is more towards the right. Or the way to think about it in both cases is you just simply want to put the more positive function first. And that's going to allow you to accomplish this task in no matter what direction you are integrating with respect to.